Today we're mostly going to be focusing on Newton's law of gravitation, sometimes called Newton's law of universal gravitation. But first off, let's kind of talk about how this relates to what we've already learned, which is centripetal force, right, in circular motion. For example, looking at the moon going around the Earth, the moon will obviously travel around the Earth in more or less a circular path. It's actually elliptical, but you get the idea, right? Since it's moving in a circle, we know from our last lesson that there has to be some force that's moving it in a circle, right? We also know that this force has to be pointed towards the center of the circle, which in this case would be the center of the Earth. So it'd be a centripetal force. And then from common sense, we know that this centripetal force has to be, hopefully you realize, this has to be gravity that's causing the moon to move around the Earth in a circle. So this is just one way that we can connect Newton's law of gravitation to centripetal forces. This gravitational force is the centripetal force that makes the moon orbit the Earth. It's also the centripetal force that makes the Earth orbit the Sun and every other planet orbit the Sun. Our solar system orbit the universe, or orbit our galaxy orbit other galaxies, and so on. Right? It's a huge idea. So Newton's law of gravitation really comes down to one thing, which is the equation that he came up with. Right? So when he was working on this law, he realized that this law depended on three things. It depended on the mass of one object, which we'll call mass 1 for now. It depended on the mass of the other object, which we'll call mass 2. And then it also depended on the distance separating the two objects, which usually what you'll see in the equation is a radius, because like we saw in the picture before, gravity as a force usually makes one object orbit another one in a circle, and of course a circle has a radius, and that radius would be the distance between the two objects. Right, so looking at these three things, I'm not going to go into detail about how he did this, but Newton came up with his law of gravitation, or the actual equation that describes it, and it looks like this. We can say that the gravitational force, Fg, is equal to, and leave some space like I'm writing it right now, it's equal to the mass of one object, m1, like we said before, times the mass of your other object, m2, over the distance between them, which is the radius, squared. All right. But there's one little extra thing with this equation. There's this capital G that we throw out in front of it. Okay. Pretty easy to understand. This right here is the mass of one object. This right here is the mass of the other object. This is the radius or distance between them squared in meters. But what's this capital G? I'll give you a hint. It's not 9.8 meters per second squared. That's lowercase g. Okay. Capital G stands for another number, but it looks a little bit more complicated than just 9.8 meters per second squared. Here's what capital G equals. 6.67 times 10 to the negative 11. And we'll leave the units off of it for now just to make the math easier. So when you use this equation here, you have to put in this number for G. Right? This mass will be in kilograms, this mass will be in kilograms, this will be in meters. This will always be 6.67 times 10 to the negative 11, no matter what you're doing with this equation. It's always this number. Let's talk a little bit more about what this equation really means, and we need to learn a couple of, well, they shouldn't be new vocabulary words, but they may be new to this class when we talk about this equation. So if we look at this equation, we've got two things. Let's ignore the capital G for now, because it's just some number that's always there. We've got two things on top of this equation, a mass here and a mass here. right? What you should know already is that, well, is what happens when I plug in or change the number of these masses here, right? So let's say I double the mass of object 1, okay? Doubling M1. What will happen to the force of gravity that object feels if I double the mass of M1? Right? Should be pretty straightforward. Fg equals g. Let's say I put in a 2 here because I'm doubling the mass of M1. Doesn't matter what M2 is. Doesn't matter what R squared is. Right? G is always 6.67. What's going to happen to the force of gravity? Well, force of gravity is going to be doubled. Right? Same goes for if I doubled this mass here. Right? I put in a 2 here. You'll see that you basically end up with this, except it says M1 here and 2 here. So your force of gravity is going to be doubled as well. What do you think would happen if I halved one of these masses? Or I took one of these masses and decreased it by 4 times, meaning I change it to 1/4. Well, it should be the exact same thing. Sorry, not the exact same thing, I misspoke, but very similar. Right? So if I half M1, it would look like this. 1/2 for M1. Alright, so what ends up happening to the force of gravity? Well, the force of gravity gets multiplied by 1/2, or in other words, it's halved as well. Very simple. Okay, when we're dealing with an equation and we're looking at things that are on top of the fraction, right? This is technically on top of a fraction over here too. We can say that these things are directly proportional to each other. There you go. Because they're both on top of the fractions. Or in other words, if I do something to these values right here, then the same exact thing happens to this value over here. I double this, this doubles. I half this, this gets halved. Right? Pretty easy to understand there. But what happens with this number, or this variable, the radius, it's a little bit different. Right? We've got a different name for it. So let's go ahead and see what happens here. We'll start off pretty simple. What happens to the force of gravity if I double the radius or I double the distance between them? That's asking the same question. Let's see what happens. Fg equals, g is always some number. I'm going to leave it out because it stays the same no matter what I do. It would be m1, m2, not concerned about those, they're staying the same, over 2, don't forget about this part, squared. Okay, so if I really try to break this down, what I'm getting is m1 times m2, let's just say that's 1, because it can be any number that I want. It would be 1 over 2 squared. Right? That is 1 over 4. So if I double the radius, or the distance between two objects, the force of gravity is changed by 1/4. It gets 1/4 as big as it was previously. Right? So you can see that doubling this does not do the same thing to the force of gravity like it did when I doubled mass 1 or mass 2. It's a little bit different. Okay. You'll notice that the reason why is because Fg is still on top of the fraction over here, but R squared is on the bottom of the fraction over here. They're not on the same sides of the fraction. We call this an inverse relationship, or inversely proportional. Right? If this goes up, I double this, this actually decreases. In this case, it decreased by 1/4. Right? Let's look at one more. Let's see what happens if I triple the distance between two objects, or triple the radius. So I would get Fg is equal to, g is some number that always stays the same, not going to mess with that. M1 and M2 aren't going to change for this problem because I'm just tripling the radius. If I put in a 3 down here for the radius, what you should see is you're going to get 1 on top again, because we can make that any number we want. We'll make it 1 because that's the easiest, over 3 squared is 9. So when I triple the radius, the force of gravity is multiplied by a factor of 1/9, or it gets 1/9 as big as it was previously. Right? The reason that it's not, so I tripled it, the reason that it's not 1/3 is because of this squared here. It makes a big difference. All right, last one. Let me go ahead and write out the equation. You can probably already predict what's going to happen here. What I've been doing so far is doubling or tripling the radius. Let's see what happens when I make the radius smaller. What do you think is going to happen to the force of gravity then, if I make this smaller? Remember, if I made it bigger, this got smaller. So if I make this smaller, this should probably get bigger. Let's see if that's the case. So I'm going to half the distance between the two objects. If I half my radius, that'd be 1/2 squared. Right. Now this starts to look a little funky. I would get 1 on top over 1/2 squared. 1 squared is 1, 2 squared is 4. I would get 1/4. Now if you remember your math rules, when I divide by a fraction, it's the same thing as, let me separate this a little bit. It's the same thing as taking the denominator here, 1, and multiplying by the reciprocal of the fraction on the bottom. Remember, the reciprocal, you flip the fraction. So it would be 1 times not 1/4, but 4/1, which is 4. So if I half the radius, if I move two objects closer together by decreasing their distance by 1/2, the force of gravity will actually go up by 4 times. It will get 4 times as big. Right? That should make sense. So we can write a couple rules here based on what we just talked about. Here's the first one. Rule 1 says increasing the mass of either object in that equation increases the force of gravity. Right? So if I have, for example, 2 planets, and one planet suddenly gets bigger than the other one, then the force of gravity between those two objects is going to get bigger. Now you can also write this rule in reverse. So you could say decreasing the mass of either object decreases the force of gravity. So you may want to make a little note of that in your notes. Here's the second rule. Increasing the distance, or remember in the equation, that's the radius between two objects, decreases the force of gravity. They don't go up or down together. The opposite effect happens. Remember, this is an inverse relationship. So once again, you can flip these words. Decreasing the distance or radius between two objects increases the force of gravity. These two rules that we just talked about should make sense to you, right? If one object gets bigger, let's say we look at the Earth compared to the Sun is much, much bigger than the Earth. It has a lot more mass. Its gravitational force is a lot bigger than the Earth's gravitational force because it has such a big mass when compared to the Earth, right? If you think about the distance between the Sun and the Earth and the Sun and Pluto, Pluto does not feel as much of the gravitational force as the Sun or as the Earth does because Pluto is so far away from the Sun when you compare it to how far the Earth is from the Sun. Right? It should all make sense. This is very logical, what we just talked about. So the last thing I'd like to show you directly relates to the little activity that you're going to be doing in class today and turning in before you leave. It will be graded based, well, most of it will be graded based on accuracy actually, because you're all going to be doing more or less the same exact thing. So if you're struggling with that activity, come back to this point in the video and hopefully this will help you. Right, so we can use this gravitational equation for a couple of different things. What we're going to look at today is finding out how much we would weigh in newtons on different planets on our solar system. So to start things off, we'll start off with the planet we're all most familiar with, the Earth, although sometimes I think your minds and brains are on different planets, but we all do live on the Earth, so we're going to start there. Right. So we can double check that this equation works by finding out our weights the old way and then comparing it to using the new equation we just learned. So if you remember, we found the weight of an object or the force of gravity on an object before it was using this equation. Fg is equal to ma, where a is equal to that magic number you love, 9.8 meters per second squared. Right. So what you're going to do in this activity is you're going to use your mass in kilograms. So the first question I'm going to get from you is, well, I know how much I weigh in pounds, how much do I weigh in kilograms? So I'm going to just going to show you real quickly how you can do that conversion. I weigh about 180 pounds. To convert that to kilograms, just take how many pounds you weigh and multiply by 0.45, I believe it is. Let me double check. Yeah, 0.45. When I do that, I get my mass in kilograms to be about 81.6 kilograms. So you should probably go ahead and do that in your notes somewhere just so you have that number because you're going to be using it a lot today on the activity. So I weigh 81.6 kilograms. So we're going to find out what my weight is on the Earth by doing Fg equals ma. My mass is 81.6 kilograms. I'm going to multiply that by 9.8 meters per second squared to find out what my mass in newtons is. Let me get out my calculator. 81.6 times 9.8. My mass in newtons is 799.68 newtons. Sounds like a lot, huh? Alright, so that's using the old way, but we can also use our new equation to find out what my weight would be, right? Remember, weight is the force of gravity. So let's go ahead and see if we get close to the same answer using this new equation. Here's our new equation. Fg is equal to g m1 m2 over r squared. So let's look at this and figure out what we're really putting into this equation. G is 6.67 times 10 to the negative 11, that number that doesn't change. Think about what these two masses are going to be. Obviously, one is going to be me. So let's say I'm mass 1. Mass 1 is me, my mass, 81.6 kilograms. Mass 2, let's think about what that would be. I'm looking at the force of gravity between me and what object? Should be pretty apparent that it's going to be the Earth. Right? So the mass 2 is going to be the mass of the Earth, which is going to be a pretty big number because the Earth is pretty large. Right? The very last thing we need to think about is, what is this radius going to be? Well, it's going to be the distance, if this is the Earth, and here's me, it's going to be the distance between the very center of the Earth and wherever I am on the surface. Right, so this would be r. In other words, I need to find the radius of the Earth. Right. Now, these numbers you're going to have to look up, and you're going to look them up for all of the different planets we're doing this activity on. So let's go ahead and look up these numbers. Alright, so I just went on Google and searched for mass of the Earth and radius of the Earth and got these numbers. Remember, mass 1 is me, 81.6 kilograms. This is the mass of the Earth, 5.97 times 10 to the 24th kilograms. I told you it was a lot. I'm actually going to use bigger numbers than this today. And then here's the radius of the Earth, which is also pretty large. It's 6,371 kilometers, which becomes 6,371,000 meters when you convert. So these are the numbers we're going to plug into this equation. So let's go ahead and solve for my weight on the surface of the Earth by using this equation. All we have to do is plug in the numbers. We don't need to rearrange. Fg is equal to, remember G, the thing in red, is 6.67 times 10 to the negative 11. Mass 1 is 81.6. Mass 2, mass of the Earth, 5.97 times 10 to the 24th. Divided by the radius, which is 6,371,000 meters. Don't forget to square that. Okay, so the only thing that makes this equation tricky is really the scientific notation. But remember, the very first thing that you need to take care of is this number that's being squared, PEMDAS, right? Do the exponent first. So when I punch this in my calculator, I'm going to square this number. I'm going to multiply these two and divide by whatever this is equal to. And then I'm going to multiply by 6.67 times 10 to the negative 11. So let me go ahead and do that. So when I put these numbers in my calculator and do all the math correctly in the right order, squaring this first, then doing this, figuring out what this is, dividing by whatever that was squared, and then multiplying by 6.67 times 10 to the negative 11, I get this answer, 800.525 newtons, which, if you go back, is very close to what we got here, 799.68 newtons. Basically both 800 newtons. So the equation works, but of course I probably didn't need to prove that to you anyways, because you always trust me, right? So what you're going to be doing today is using this equation right here to find out what your weight would be on the various planets in our solar system. Some it will be very similar to your weight on Earth, so you could, basically jump as high as you normally could and do all the other stuff. Some it'll be a lot smaller, meaning you could jump super high. Others, it's going to be a huge number. Your weight would be gigantic, and you might actually even die because your weight is so large, right? And you'll figure out which planets those are by the end of the activity today. But before you start on the activity, don't forget to answer the 4 or 5 questions that accompany this video, right? The easy ones that are based on your notes. You can go ahead and answer those and then get started on the activity.